Let's examine how frames flow through a switched network and how MAC addresses are learned by those switches. On screen we have three different switches, and I included a hub as well. And this reminds us that a hub does not have a CAM table. It doesn't have a content addressable memory table like a switch does. A hub doesn't learn anything. We call it a bit spitter. It takes bits in on one port and it just regenerates them out of other ports. So it's not really making intelligent forwarding decisions. It's a layer 1 device. The switches, they are layer 2 devices. Let's say that we have a frame, it's an ARP packet specifically that's going to be sent out in the network, but at layer 2, at the frame level, the source MAC address is the MAC address of PCA. PCA, it's wanting to communicate with PCC as an example. And it knows the IP address of PCC, but it doesn't know the MAC address. How does it learn that? It can send out an ARP broadcast. An ARP broadcast, that's an address resolution protocol broadcast that gets flooded throughout a broadcast domain, and we're asking the question, can somebody tell me the MAC address that corresponds to this IP address? That way we can form a frame that has an appropriate destination MAC address. Right now, PCA doesn't know the MAC address of PCC. So in this ARP packet, we have a source MAC address of all A's, and these would not be MAC addresses that you would find in the real world. I just used all A's, all B's, and all C's just so that we could easily look at a MAC address and identify it so that we could associate it with one of these PCs. Now the destination MAC address, this is the MAC address that you would see in the real world. It's all F's. And all F's MAC address is a broadcast MAC address. And there will never be a device on your network, like a PC with a network interface card, that has an all F's MAC address, so it will never be learned by a switch. And what does a switch do when it receives a frame and it doesn't know the destination MAC address of that frame? It hasn't learned that MAC address is living off of a particular port. The switch floods it. And by flooding a frame, we mean that we're going to send a copy of that frame out of all of our switch ports other than the port that the frame was received on. So in the real world, you really would have a destination MAC address of all F's. Let's see how this frame flows through the network. The frame goes into switch 1, and even though we're destined for the all F's MAC address, switch 1 notices the source MAC address. It's all A's. And it learned that that source MAC of all A's, it came in on switch port 1. And it makes a note of that in its CAM table. This is another way of saying the MAC address table. CAM, again, stands for Content Addressable Memory. We could use those terms interchangeably, though, CAM table or MAC address table. Now that the switch receives this frame, it learned something. If anybody ever wants to get to PCA, we now know where its MAC address resides. We don't have to flood a frame going to PCA. But in this case, we're still trying to get to the all F's MAC address, and we don't know it, and we will never know it. We're going to flood it out, all of the ports other than the port that the frame was received on. So switch 1, it floods that frame out of port 2, and it goes into switch 2, port 1. And switch 2 says on port 1, I just saw this frame come in, and it had a source MAC address of all A's. And this is an important point. PCA is not directly attached to switch 2, but still it's available off of switch 2's port 1. That means that switch 2 wants to add to its CAM table that all A's MAC address is available off of port 1. Sure, it's a switch hop away, but that's okay. It's still available off of port 1. Switch 2 is going to now flood this frame. It goes out of ports 2 and 3. When it gets to switch 3, it came in on port 1. Switch 3 makes a note of that. Switch 3 says, I just learned off of port 1 that there is a device with a MAC address of all A's. It adds that to its CAM table. Now the hub, it doesn't learn anything. It's just a repeater. And it's going to just repeat those bits and send them down to PCB, which will say, this isn't for me, and it will discard it. Switch 3, it's going to flood that frame out of port 2. It's going to go to PCC, and it's going to say, that's not for me, and it's going to discard it. But that completes this initial ARP broadcast from PCA out to our network. And over time, the other computers on the network will start to speak as well. Let's say that PCB sends an ARP packet at some point. We've got a source MAC address of all B's, and we're going to a destination MAC address of all F's, the broadcast MAC address. The packet goes through the hub into port 2 of switch 2. Switch 2 is then going to make a note in its CAM table that off of port 2, I've got a MAC address of all B's. It then floods that frame out of ports 1 and 3. This is going to cause switches 1 and 3 to learn how to reach the all B's MAC address, and they're going to flood that frame out of their ports. And those PCs, PCA, PCC, they're going to say, this frame isn't for me, and it's going to discard it. But in the process of doing this ARP, notice what happened. All of the switches now know how to get back to the MAC address of all B's. And for completion's sake, let's say that PCC sends out an ARP packet. The source MAC address is all C's, the destination MAC address is all F's. We go into switch 3. Switch 3 learns that the all C's MAC address lives off of port 2. Switch 3 floods that out of port 1. It goes into switch 2, port 3, and switch 2 makes a note of that available off of port 3, we've got the all C's MAC address. It's going to flood that frame out of ports 1 and 2. The hub is not going to do anything other than just regenerate those bits and send them down to PCB, but switch 1, it made an update to its CAM table to say that the all C's MAC address, the way we get there is we go out of port 2 on switch 1. The frames go down, they hit the PCs discard them, and at this point, we have fully populated the CAM table for all 3 of our switches. Of course, in the real world, we would probably have lots of additional devices, not just 1 or 2 PCs hanging off of a switch. We would have lots of PCs potentially, and we could have larger CAM tables, but this illustrates the logic of how a CAM table is built. Now that we have a populated CAM table, let's send out a frame that's not a broadcast this time. Let's say that PCA is sending a frame to PCC. In other words, the source MAC address on this packet is the all A's MAC address, the destination MAC address is the all C's MAC address, and we're going to see this time the frame doesn't get flooded. PCA sends out this frame into the network, into switch 1. Switch 1 interrogates its CAM table, and it determines that the all C's MAC address is available off of port 2. And even though we only have one other port on switch 1 in this example, we could have 10 other ports, and switch 1 would not flood that frame out of all of those ports, because it knows that to get to the all C's MAC address, we just go out of port 2. That's what it does. It sends the frame out of port 2. It goes into switch 2. Switch 2 looks at the destination MAC address. It's all C's according to its CAM table. That's available only off of port 3. No need to send it out of port 2. We send it out of port 3 into switch 3. Switch 3 says, the all C's MAC address, I learned, that lives off of port 2, and it forwards it to the destination PC. That is an overview of how a switched network is going to learn where different devices live. The switches learn based on source MAC addresses. Then, when a frame comes into one of those switches, trying to get to a destination MAC address, and that MAC address has been learned earlier because it was earlier a source MAC address, the switch can intelligently forward that frame out of an appropriate port instead of having to flood it.